Hey everybody, welcome back to another lesson in data structures and algorithms. This is our final unit on dynamic programming. Today we're going to be looking at kind of an introduction to dynamic programming. We'll start with kind of a classic first problem. We'll look at the Fibonacci sequence. And then we'll look at a more, also slightly more interesting problem. So first of all, what is dynamic programming? Well, dynamic programming is kind of the art of constructing solutions to problems by building up from a base case. And that's kind of the working definition I want to go with. This idea that when I solve a problem dynamically, I'm solving a base case problem, a problem that's really simple, and then using that answer to build up the answer to gradually more and more complicated versions of the problem until I reach the level of complexity I'm looking for. So let's start with the Fibonacci sequence. Classic way of teaching students recursion. So let's say I've got a method, public long fib, and I'm just going to go ahead and generate this in just a simple class here. So I've got a project called, let's call it Dynamic Problems, and we've got a class called Fibonacci. And I'm going to just type this up right quick, and we'll kind of explain it as we go along. All right. So this particular method, we're just calling it fib. It's going to take in a number that we're looking for. I'm going to use long because it's a little bit, it's twice as big as an int in the number of bits, so it can store quite a bit bigger number. So the Fibonacci sequence traditionally starts with 1. So you have like 1, and then 1 for the second term, and then 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8. So you see, we just keep adding the two previous terms to get the next one. Well, this can be done recursively in a nice clean code. So I'll just say that if n is equal to 1, because the first term of Fibonacci is a 1, we'll do 0. We'll say it starts at term 0. So if n equals 0 or n equals 1, then I'll return n. So we'll say the 0 term is 0. So we're making our Fibonacci start like this. It'll be 0, then the first term is 1, and then term 2 would be 0 plus 1. So that'll work nicely. All right, so we're just going to return and we're done. Else, okay, if it's not that value, I'm going to return a recursive call with the two numbers before it. So let's say I call this with n is equal to 2. So since n does not equal 0 or 1, I will return fib of 1 plus fib of 0. Well, fib of 1, when you call it with 1, 1 is equal to 1, so it will return 1. And fib of 0 is equal to 0, so 1 plus 0 is 1. What happens if I call this with 3? So f of 3, since it's not 0 or 1, I will return f of 2, that's 3 minus 1, plus f of 1. Well, f of 2 is f of 1 plus f of 0. And then f of 1 we already know. We have that as well. Here is f of 1 returns 1, so that answer is going to be 2. And it just kind of builds up like that. See how the recursion works. Well, so a lot of computer science teachers, I myself am guilty, love to introduce recursion with this Fibonacci stuff. It's really clean code, easy to read, good way to understand how recursion works. However, it's got one problem. It's horribly slow. So let's try, I'll make a instance of the class, and then let's see here. Let's try and find like the 8th Fibonacci number. Well, let's see here, 21. So do we believe that? Let's find out. So let's see. We said the 0th Fibonacci number is 0, and then the first is 1, the second is 1, 3 is 2, 4 is 3, 5 is 5, 6 is 8, 7 is, looks like 13, and the 8th is 21. All right, cool, it worked. And it didn't take it too terribly long. Let's find out what the 20th Fibonacci number is. Okay, 6,765. Again, not too long, right? So let's take a look at the 50th Fibonacci number. I think that will still fit in the long. Fibonacci gets really big really fast. You have to start using something like big integer. Let's do the 50th Fibonacci. Oh, wait a minute. Huh. Wow, it slowed down pretty quickly, didn't it? The 20 was really almost instant. This is taking a while. I'm going to pause this recording here and tell you how long it. All right, and we are done. It's a pretty big size number. Definitely, what is that, in the thousands, millions, trillions? You can see by the clock down here on my screen. I hope you can see that. It's been a few minutes. Okay, so that was surprising how long that did. Well, that's just based on the O-in ratio. So it turns out the O-in runtime complexity. It turns out that the O-in for this is O2 to the n. So when I do that, that is growing. The rate of time it takes to calculate is growing exponentially. Not a good O-in at all. All right. Let's talk about why it's so slow, though. Sometimes it's difficult to understand where these O-ins come from when it's recursive. But let's just look at one situation when I want to calculate the Fibonacci value, the 6th Fibonacci value. Well, we know that since it's not 0 or 1, it's going to call Fib 5 and Fib 4. But Fib 5's got to do 4 and 3. Now, what's interesting is that, this Fib 4 has to be calculated here, but it also has to be calculated over here. And so all of this work that we have to do, all of this calling here, I have to do that again all the way over here. It doesn't remember. There's no, what we call memoization. It doesn't remember what that value is. So I'm sitting there recalculating things many more times. I'm making the computer do many more calculations than is necessary if it would just remember what it's done, or do them in the proper order, I should say. So instead of working from 6 down, which is bad, and then feeding it back up recursively, let's work from the bottom up, okay? So we're going to do this a different way. So let's go back to our Fibonacci algorithm, and let's do it dynamically. Now, most of the time that we're going to solve a dynamic programming problem, we're going to need to have either an array or a matrix to store the information. It's possible we could use some other kind of data structure. But for us, we're always going to have either an array or a matrix to keep track of our results. So I'm going to use an array of longs, and I'm going to make my array one index more than the value I'm trying to get. So for example, if I want the first Fibonacci number, I need to calculate the Fibonacci number at 0 and at 1. This is very common with dynamic programming. You'll see that we make an array one longer than the number we're trying to calculate to, because the index of the array will be the value in that I'm calculating. So for example, if I want to calculate the 5th Fibonacci number, that I'm going to store that answer in index 5. So that's why I have to do n plus 1, because we know if we want an array that has an index of 5, I actually need to make it 6 long. So now what I'm going to do is I'm going to store in the first 2 numbers of the Fibonacci sequence. So I'm going to make the 0th index be a 0. And the first index will be a 1, just like we did on our recursion. Then I'm simply going to loop through, starting at the bottom, not at the top, so I don't do any repetition here. So I'm going to start with I at 2, because that's the first value I need to calculate. I'm going to run as long as I is less than or equal to the n that I'm trying to calculate, which would be actually the last index, because we made our array of length n plus 1. And I'll say dp bracket I, dp for dynamic programming, equals dp bracket the dp bracket I minus 1 is the Fibonacci number right before it. Well, remember, when I starts at 2, we've already calculated the dp of 1. Plus, I need the 1, 2 before it, so I'll do I minus 2. And there we go. Well, when we're all done with that loop, I simply have to return the DP at index n. Let's try this one out. Oh, let's see here. Causal lossy conversion from long to int. Oh, okay. Well, let's see here. We need to go ahead and force that casting. That's because you can't do anything bigger than an integer for the size of an array. And that's okay. All right, just fill that in right quick. All right, just a little force casting there. All right. All right, let's give it a try. Earlier we did the 50th number, so let's try the 50th number again. Basically instantaneous. We cut down the amount of operations dramatically. So let's talk about the runtime for this. Well, the runtime, as I said for the other one, if you count all the different times you have to go backwards, for every number we send, we have to fork off over and over again by 2. We have to double the number of the number of computations for every n I go up. For example, if I had 64 calculations to do n, well, then to find n plus 1, I know I got to find the value at n, and I got to find the value at n minus 1. And this here would be roughly like 32. But you can get the idea that we're taking this value and almost doubling it. So approximately, it's doubling every n, which is, we know, 2 to the n. Compare that to this algorithm here. I have a copy of it here. I know I don't have the... Oh, there it is. If I just made the variable an int right from the beginning, which makes sense, that wouldn't cause that problem. Compare that to, what do we have here? We create an array of size n. Well, that's just on. And then I loop from basically the beginning to the end. That's another on. On plus n is just on. So this is a ton faster, right? Well, let's think about something. If I have an algorithm for computing the nth Fibonacci number that runs in a runtime of O2n and can compute the 10th Fibonacci number in 2 seconds, how long would it take to do the 100th? Well, all right, let's go through that. I know that 2 to the 10th corresponded with 2 seconds. How would that compare with 2 to the 100th? How many seconds would that be? So I get 2 to the 10th times x, when I cross product, equals 2 to the 101. Which means x is equal to 2 to the 91st power, which is approximately, if I do the calculations, that's 2 to the 91 seconds, right? Oh my goodness. 7 times 10 to the 19th years is what I'm seeing in my notes. That's how long that would take. That is brutal, right? Not at all the case when doing ON though, because if it took 2 seconds to do 10, and then we have 100, well, that's just a linear increase in time. That's just, well, I mean, that's just 10 more seconds. That's just timesing that by 10. That'd just be 20 seconds. So the change is very small there compared to when it's 2 to the n. Very different situation. All right, let's take a look at another problem, another kind of classic intro to dynamic programming problem. So here's my problem statement. Given a list of coin denominations, find the amount of each coin type needed to make the needed change so that the fewest number of total coins are used. We're going to assume an infinite amount of coins are available in each denomination. So we're going to solve this problem in 2 parts. Given a list of coin values, we're going to find the minimum total number of coins needed to make the change. That's going to be the first part. That's the hardest part, I think. Then the second part is we have to use a technique called backtracking to read our resulting array to find what those amounts of change should be. So let's start with this situation here. Suppose that the coins we have are in denominations 1, 3, 7, 8. So I don't know, this is some weird country where they have cents of 1, 3, 7, and 8. And that's kind of part of the problem, is that we're not going to be set with specific values. But these could be anything. These could be weights or something like that. So it's still a worthwhile problem, even if we're not using the standard denomination amounts. All right, suppose we want to find how to make 15 cents in change in the least amount possible. Well, this is how we're going to do it dynamically. So in order to solve this dynamically, I need to make an array that is equal in size to a size big enough to where the last index is the value I'm looking for. Remember, we're looking for 15 cents, so I want that solution to be in column 15 of this array. And I'm going to fill everything with some value infinity. So just put I for short right now. Now, in order for this to work out, I need to be able to do these two things. First, I have to be able to solve some base case. I need to be able to solve this problem quickly and easily at a base value, say 0. Next, I need to determine a formula that allows me to take the information that I currently have built up to some case n, and use it to solve the case for n plus 1. If I can do that, then I can build the entire array up from the beginning to the end. So first, base case. For me, that's when I'm calling this K, all right, because we're going to let K go from 0 to 15. So this is my base case. Can we solve that? Can we determine how many coins it will take out of our denominations 1, 3, 7, and 8? How many coins do I need to give a customer back 0 cents in change? Well, I think that's pretty obvious. I don't need any coins, so it's 0. All right, so we have a base case. Check. We've done it. Well, let's continue to see if we can use that to generate some more answers. After a few iterations of this, maybe we can come up with a formula. So let's look at the next one. All right, so I've got all my I's. Remember, we started this fill with infinity, right? And if there's ever a coin denomination we just can't make, we would actually end up with it still being infinity. You know, and since we have a coin denomination of 1, not going to happen. But if we had only had denominations 3, 7, and 8, then you would say, well, we can't actually make 2 cents in change, right? Okay, so let's take a look, though, at this situation here. When we have change of 1, well, there's only one denomination that can give me a change of 1 cent. Because there's only one denomination that is less than or equal to this change amount. Remember, it's the index, right? I'm looking at K equals 1. The index of the array is the amount of change trying to make. So I really only have one coin type to consider. So since I've only got one coin type to consider, I just need to see, hey, how many of those coin denominations do I need? Well, to make 1 cent out of 1 cent coin, I just need 1. So we'll fill that in. And we'll go now to the second one. All right, look at the second one. Again, there's only one coin type that has a denomination that is less than or equal to 2 cents. So that's the only coin I'm allowed to use. So how many 1 cent coins does it take me to do this? Well, it takes me 2 of them, right? And let me talk about how I'm getting that figure. You know, you might think, well, just, 2 divided by 1. But what I'm going to do is I'm going to work using this information here. I'm going to say, well, 1 cent coin that means I need to add 1 cent to the value that's 1 index behind me. So I go 1 cent backwards in time. That way. Look at it and take this amount and say, well, because this is only 1 cent away, I just need to add 1 cent to that value, 1 coin number to that value. That tells me how to get this amount. So that's 2. So a little bit different way of thinking about it. All right, let's go on to the next one. All right, now let me fill this in. Actually, I got 1 and 2. So this is finally things are going to get a little more interesting because I actually have somewhat of a choice here. We have 2 denominations to choose from now, a 1 cent coin and a 3 cent coin. So let's talk about which one I would use, and we got to think like a computer, okay? So first thing I'm going to look at is the 1 cent coin. because 1 cent is less than or equal to the 3 cents I'm trying to make, I'm going to go back 1 cent. That means one index. So I'm going to go back. Remember, we're at k equals 3. I'm going to go back to k minus 1. And I'm going to look at that coin number, and I'm going to say, okay, let's add 1 to that, and that gives me 3. So I'm going to put 3 right there. And the reason why I'm putting 3, we haven't discussed this yet, is because I'm actually comparing it to the value that was used to be stored there. The value that used to be stored there was some big number we're calling infinity, and 3 is less than infinity. So we've momentarily gotten a solution. Next, I'm going to check the next coin, which is coin 3, and I'm going to do the same process. Because I am looking at a coin of value 3, I'm going to go back 3 indices. So when I go back 3 indices, I see that there's a value at 0 coins to make 0 cents. And since 0 cents plus my 3 cent coin equals my perfect amount, I see that I would only need to add 1 coin to this value, which is less than the value I currently have stored there. So I'm going to replace this with a 1. And there we have it. We've solved the case for 3 cents. All right, what I'm going to do is I'm just going to copy this wrong thing. I'm going to just copy this kind of spreadsheet I've got going here, this representing our array. Oh, didn't quite copy there. And let's fill in some more. Okay, so let's continue this process. On the next one we're looking at 4 cents, right? 4 cents, we've got to make 4 cents and change. So I can choose from the 1 cent coin and the 3 cent coin. Can't use the 7 and the 8 though. So I look at the 1 cent coin and I go backwards 1 index to index 3, and I see that there was only 1 coin needed there. Since there's only 1 coin needed there, I can add 1 more coin to it of 1 cent to make 4. So that makes this value 2. Next, we check the 3 cent coin. So since a 3 cent coin can give me 4 cents, it fits in the 4 cents, I'm going to go back 1, 2, 3 indices to this 1. And I see that it took me 1 coin to make 1 cent, and 1 cent plus 3 cents is 4. 1 coin plus another coin is 2 coins. So it turns out there's actually 2 different ways I could have done this. I could have done it with getting a penny added to a 3 cent coin, or a 3 cent coin added to a penny, but that's the same solution. So it works perfect. Let's do it again. Okay, so next I'm going to look at the 5 cent coin. Once again, I've only got 2 coins that I can. Remember, our coin denominations are 1, 3, 7, and 8. So I've got 1, 3, 7, and 8. So for the 1 cent coin, that will fit in 5. I go back 1 index to 4, and I see that I can make 5 cents by taking the perfect, remember, the solution that's in index 4 is the best solution. 4 cents plus 1 cent is 5. That's a total of 3 coins. I could also look at going back 3 indices, 1, 2, 3, and adding 1 coin to that amount, because 2 cents plus 3 cents is 5 cents, but that gives me the same answer. All right, let's try again. Just keep on adding to our little tally here. All right, so now our solution here was 3. And remember, our coin totals that we have available are 1, 3, 7, and 8. 1, 3, 7, and 8. So I still can't fit anything but the 1 cent coin and the 3 cent coin here. But we can look at those. So if I go 1 index back from the, remember this is k is equal to k is equal to 6, is that right? Yeah. K is equal to 6. If I go back 1 index to index 5, I can see how many coins were there, which was 3. Adding 1 more penny would give me 4 coins, which is definitely less than the infinity I had before. But also, since I have a 3 cent coin, I can look at going back 1, to 3 cents, and I see that I made a solution there of only 1 coin. And 1 coin plus 1 more coin is only 2 coins, which is less than the 4 I just found. So we started at infinity, we improved it to 4, now we improved it to 2. All right, next we take a look at the value of 7. For the 7, I can go back 1 coin and add a penny to get 3. But I could also go back 3 indices and add 1 penny to this and also get 3. Not 1 penny, 1 3-cent coin. But now I can actually go all the way back to 7 indices and see that there were 0 coins to make that. So I only need 1 coin to make 7 cents. The 8-cent coin is going to be the same procedure. I'll look here and say I can add a penny to take 2 coins. I go 1, 2, 3 cents and make it in 4 pennies, 4 coins. I don't want that. I can all go back to here to the 1 cent penny and add a 7-cent coin, or I can go all the way back to the beginning and add an 8-cent coin, which is what we'll end up doing. All right, let's try the 9 now. For the 9, I have the full complement of coins at my disposal. Let's check what happens to add a penny. Go back 1, I add 1 to 1 coin that's there. I can make 9 cents in 2 coins. Go back 3, 1, 2, 3. Ooh, I can make 9 cents this way by making 6 cents first and then adding 3 more, but that would take me 3 coins. Let's go back 7 to here. That would take too many coins as well. Let's try adding 8. Well, I could add 8 to the 1 coin here, but that's the same answer. It's just 2. All right, let's try 10 now. Okay, at index 10, I go back to index 9 and say, okay, I can make this 10 cents and by adding 1 coin, the amount of coins I had at 9. I can also go back 1, 2, 3, and oh, look at that. I can make it in 2 coins by taking the amount of coins I had to make 7 cents and adding 1 3-cent coin to it. I can also go back 7 and do it this way. That's the same answer. There's still just 2 coins. Or I can even go back 8, but that's not an optimal solution. Next, we go to the 11. On the 11, I can go back 1 cent and see I can do it in 3. I can go back 1, 2, 3 and see that I can actually make it in 2 coins. That's an improvement. And then I can go back 7 to index 4. That would be 3 coins. That's not good. I can go back 8 to index 3, but that's the same solution we got earlier. Now we look at the 12. For the 12, go back 1. I can do it in 3. That's an improvement of infinity. Go back 3. 1, 2, 3. That's the same. Let's go back 7. 1, 2, 3, 4, 5, 6, 7. That'd be 4. Let's go back 8 cents, and that'd be 3 as well. The 13, we can see we can just add 1 coin to one before it, making it 4. Or I can go back 1, 2, 3, and add 1 coin to that. That's better. That's only 3 coins. I can also go back 7, which would be here to 6. That also is 3 coins. Or I can go back 8, which is here to 5, but that's not optimal. All right, we'll try 14. I can go back 1 to the 3 and make that 4. I can go back 7 value, and it looks like I can get it in 2 steps. That is definitely better. Now let's try the 15. I can go back 1 coin, make that 3. I can go back 3, 1, 2, 3. That would be 4. That's not better. I can go back 7 and add a 7-cent coin to an 8-cent coin. Gets me the answer in just 2 coins. So that's the optimal solution. So that's the first part of this algorithm, is we found the optimal number of coins, but we have to use backtracking, and we'll come back and discuss that in a minute. But what we want to discuss now is what exactly formula was I using to do this. So first of all, we had an if statement. We said we're going to loop through the indices, and we said, if the coin value that we're looking at is less than or equal to the amount of change I'm making, which is my index K, then I'm setting the value at that value there. I'm setting the value in my array, K, that index, to the minimum of what's currently there. And one more, that means adding 1 coin to the solution that was the value of this coin back in indices. And that's one of the reasons why it's so important to do this check here, because we don't want to go out of bounds. And I do that for every coin in my denominations list. Let's take a look at how to solve it. Okay, so I'm working in my dynamic problems little Blue Jay project here, and I'm just calling this coin problems. So public coin problems. Public, we'll say public void solve. And we'll go ahead and get the value. I'm going to want to be able to get the array as well. We could do this in a series of different methods. We could write it as a class. For now, I'm just going to return the value for now. So public int, that's going to be the minimum number of coins that it takes. Public int solve. All right, I'm going to make a constant here called infinity. And infinity will be like 100,000. I don't want to make it as large as the maximum value for int, because then when you add 1 to the largest max value for int, you'll actually get a negative min value, which would screw up the whole algorithm. So I need to have some room to add to it. I could also make it like a long to get more room, but we'll just stick with that. All right, next I need to make some denominations. Oh, I need to also code a little better. There we go. So let's make some denominations. I'm going to say int denominations are, well, I'll just say values. How about that? Values is equal to a new int array. And what were we doing? 1, 3, 7, and 8, right? Okay. So now that we've got that, I'm going to create my array. Well, you know what? I need to have an amount of coin that I want to get. So I'm going to say int, let's call that change. So let's make our DP array, as I call it. Int DP is going to be equal to, and we want the last index to be the index number that is the change. So we're using our index to represent the change that we're returning. So that is equal to new int change plus 1. Now that I've gotten that, I am simply going to fill that array up. So I'll say for int I equals 0, I less than dp.length, I plus plus, dp bracket I is going to be equal to that infinity that I just made. All right, so now they're all in infinity. Now I need to set my base case. Well, my base case was that when they're, you know what, if you want no change back, I know how much change it takes me, just 0 cents. Now that I've done that, I simply need to do a loop through here and solve it. So I'll say for int k equals 0, actually 1, we're going to start at index 1, k less than the length of the array. I'm going to solve it at each index, but I got to loop through each coin value. So I'll say for int v equals 0. Actually, I'll just do a for each loop. For int v in values, I'm going to say dp bracket k is equal to math.min. Oh, you know what? I forgot to check if the value fits in the array. So if, we got to make sure that the value is less than or equal to the amount of change I'm returning, which is the index k. So if value is less than or equal to k, then I'll say dp bracket k is equal to math.minimum of the value that's currently there. That's what we discussed, right? We've got it right down here, I think. And then we got to subtract then we're going to check that to, I forgot the add 1 over here, y'all. Got to add 1 because we're still adding one more coin to it, right? So the value that is, so we're going to compare the current best solution at index k to what happens if I add 1 coin to the optimal solution, that coin value away back to the left. All right, when we're all done with that, we'll just return dp bracket k. And hopefully that will work. It doesn't know what K is anymore. I got to do change, right? There we go. And we'll try it. All right, so I've got a new coin problem here. I can type in any of the different values that we found. Let's try 15. It does say it can do it in 2. Let's see, 12 was 3. Let's try that one. So let's say, how much to do 12? It says 3 coins. Obviously the 9 should be 2. So I would say we solved it. So I'll just put that up again just for your glorious looking at. We made our different, we made an array of the different values. We made an array equal to the amount of change I want plus 1 so that the change is, the last index is the change I'm solving. Filled it with infinity. And then at each index in the array, after solving the one at 0, I start at 1. For each index, I check for every coin value that I have if the value fits in that amount. If the coin is less than or equal to the amount of change I'm making at that moment, I see if it makes for a better solution using our formula. And that's it for this lesson. We'll look at backtracking in the next one.